So this topic is about Gauss's law. Why is Gauss's law important? Because we know that charges, they can create E field. If we do not see any charges, we see this E field. We know for sure that there must be some positive charge here because we see E field coming out from that area. And we know for sure that there must be some negative charge here because we know that E field, they ends here, they all come toward this direction. And we know probably there's no E field in between whatsoever because those E field lines, they do not start or end anywhere in between, okay? So that's what Gauss's law tells us. Basically, it says that if you choose any closed surface, it's not like an open piece of paper. It has to be a closed surface, closed in all the directions, no matter a box, a cylinder, or a sphere, or any arbitrary closed shape, okay? If you choose those closed surface, what you're going to get is that, for example, you choose this closed surface, and then you calculate the E field flux coming out of that, which is the area integral of E with small patches of dA on the surface of that shape or closed surface shape. And then if you do that integral, you're finding out the total flux for that closed surface is going to be equal to the amount of charge enclosed inside over a constant epsilon 0. So without any calculation, we know that it's going to be positive. And also, this is called the E field flux. We know the E field flux for this purple surface is going to be positive because we have E field lines coming out. And that's how we know this is positive, and that means the charge inside is positive. Similarly, in this region, I can choose an arbitrary closed surface like that. We see E field lines coming inward, and this integral is negative because the normal direction of the surface is outward, but the E field are inward. And this gives you the flux less than 0 for this orange surface. Because of that, this is negative. We know for sure that inside we have some negative charges. What if we are going to choose an arbitrary surface like this, the green surface? Now we see that we have E field coming inside from this end and going outward. Nothing stops inside, and there's nothing new being generated inside. And the total net flux, in this case, is equal to 0. The flux is proportional to the number of E field lines going out or coming into the surface. In this case, whatever comes in goes out. The total net flux is 0. Something negative here, something positive here. And that tells us there's no charge in this region. Also, there's no charge in this region, this region, or this region. The only regions which has charge are here and here. Okay? Conceptually, we understand Gauss's law, and for calculation, we can use it to calculate E field for us so that we do not have to always consider an object as infinite number of small dq and finding out the small amount of contribution of E field and integrate to get the total E field. So, the Gauss's law is true for every situation, and it is only useful for very symmetric cases. Okay, so for example, if we have an infinitely long charged wire, it's a wire, it has a uniform charge on top of it, and it is infinitely long, that's not end, okay? So, and because it's infinite long, the total amount of charge is infinite. However, we know the charge density lambda equals to the certain amount of Q or delta Q from here to here over the length from here to here. If you know lambda, multiply the particular length, you find out the total amount of Q in that part. If you know delta Q for this part and you know the length, you can find out the lambda. Lambda is equal everywhere, okay? In this case, we know the E field, if that's positive, we know the E field coming out of this infinite long rod is going to move outward. And you have an infinite amount above and you have infinite amount below. So there's no reason for the E field to bend upward or bend downward. The E field is going to go away perpendicular to the rod. And that's true at the center, but because it is infinitely long, every point can be considered as a center. So the E field goes out like that all over the place. Okay? And then it is not only on this plane, around this rod, the E field goes forward that way and coming backward that way. And this shape has a particular symmetry which looks like a cylinder. In order to solve this problem, keep in mind when we apply Gauss's law, we need two situations. We want either the E field to be perpendicular to the surface. If the E field is perpendicular to the surface, the E field is parallel to the normal direction of the surface. If the E field is parallel, then the E dot n, the dot product of E field with your normal direction is equal to the E field itself. Okay? Or we want E field to be parallel to the surface. If we choose E field to be parallel to the surface, the E field is perpendicular to the normal direction. When you have a surface, that's your surface, and that's your normal direction. If your E field is perpendicular to the normal direction, if your E field is parallel to the surface, then nothing penetrates the surface. And in that case, we have E dot n equal to 0 when these two vectors are perpendicular to each other. So you have a maximum amount of flux when E field is perpendicular to the surface. You have zero flux when E field is parallel to the surface. If we choose the surface this way, this very complicated integral is going to become something simple, because this can be simplified into E itself. And we also want the E to be uniform on the surface, at least on part of the surface. If E is uniform, we can take the E out for this integral. So also we want the surface to go through point of interest. For example, in this situation, if I ask you to find out the E field at this location P, I would like to choose the Gaussian surface, which is a closed surface. I want the surface to go through this point. Closer or further away won't help. I need the surface to go through this point. And I need the surface, you see, to be perpendicular to the E field. When the E field is this way, I want the surface to be like that. Okay? But the E field is not only in this direction, but in all the direction radiating outward. So we want a cylinder surface. So the surface of this entire cylinder, everywhere you are having the E field penetrating outward perpendicular to the cylinder. That's not closed yet. For a closed surface, we want to close it with a flat top, and we want to close it with a flat bottom. On the side walls, we have E field perpendicular to the surface. So for the side, we have integral of E dot n dA simply equal to the E field taking out and integrating the area, which is equal to E field multiply the side area of this cylinder, which you can know easily, equal to 2 pi r multiply height of L or H. Okay. How about the top and the bottom? For the top surface and the bottom surface, because the E field is parallel to the surface and the E field is perpendicular to the normal direction, the flux equal to 0. So the total flux is then easily this. All we need to do is to set that E multiply E multiply 2 pi r h, which is the side surface of this cylinder. We set that equals to the amount of charge inside over epsilon 0. What's the amount of charge inside? The amount of charge inside is this charge. And that's equal to the charge per unit length multiply this particular height. That's the amount of charge, not including anything above or below, over epsilon 0. By doing this, move this to the bottom of this equation, we can solve for E. Okay? Keep in mind, we want the E field, we choose the surface so that it's either going to be perpendicular to the E field or parallel to the E field. That's how you can simplify this integral, so that at the end you have either 0 on top and bottom, and you have something as simple as the E field value at this location, E value, multiply a particular area. And in this case, it's the area of the cylinder. And then you can imagine if you have a sphere, no matter it's fully charged, or if you have a shell, it's empty inside, but you have charges on the outside, or if you have some other spherical shape, okay, then you have your all inside the sphere right here. You have charges all over the place, but try to figure out the E field here, here, or here. You would like to choose the surface to be a sphere, so it is going to be perpendicular to the E field. E field is going to be radiating out in all the directions, and then you want a surface to go through the particular point P and be symmetric and the proportion perpendicular to the E field. And in this case, you want a Gaussian surface to be going through that point P and perpendicular to the E field, because inside the charged sphere you have E field all going away in the radius direction like that. Okay, and then once you have that, the integral of that becomes simply E multiply the area. The area of this pink sphere, this area, and this area. And what's really important is to figure out the amount of Q inside. In these two cases, it's easy. All the Q's are inside. In this case, it's not easy. Not 100% of all the charges are inside. What's really inside is only a small portion of the total. You have to use the volume inside instead of the total volume of the sphere to figure out the Q inside. Here, this is your inside amount of Q. Here is your inside amount of Q. And then you can set up an equation for E field and solve for it. Okay? And whenever you use this Gauss law, it is a big no-no to write E equal to KQ over R squared and plug that in here. No, we do not know what E value is. We set up an equation to eventually solve for E. E is unknown. It's a big no-no to memorize E equal to KQ over R squared and plug that in here. Okay? We use this and simplify that into E multiply a particular area, the E multiply a particular area, and we set that equal to the amount of charge inside over a constant. Then we have an equation, and then we can solve for E. The last example is what if we have a infinitely big flat sheet of paper which has evenly distributed charge everywhere, okay? And then we have E field perpendicular to the surface going away from it, going away from it. In that case, we would like to have a Gaussian surface, which is going to be, you can choose a cylinder in this orientation, penetrating the surface, okay? So that's the amount of charge inside. And at the front surface, you have E field going this way. At the back surface, you have E field going that way. So the side view look like this. You have flux going out this way, you have flux going out this way. But there's nothing going from the side. In that situation, you have your E field multiply one area, two area. That's the integral of the flux equal to the amount of Q inside over epsilon 0. And the amount of Q inside is only this part, okay? Which is equal to the surface charge density multiply the area of this part. And then you can solve for your E field. If for some reason E field is only in one direction, like on the surface of a metal, or for a parallel capacitor for two parallel plates, outside there's no E field, then you do not have 2A, you only have 1A. So this summarizes the important concept and some examples of Gauss's law. And that's the end of this video.